everyone. In this video, you're going to learn a little bit more about rational functions and what we call a discontinuity. So up until this point, we've been graphing basic rational functions, but you've already been introduced to what I mean by discontinuities. A discontinuity is just a break in the graph, okay? Now, the breaks in the graph, though, coincide with the domain of the rational function. So remember that a rational function is defined only when its denominator is non-zero, or when the denominator is not zero, okay? So what happens when the function is undefined? What happens for those values of x where if you did plug them in to the equation, you get 0 in the denominator? Well, I hope that you're answering, first of all, that there is a break in the graph, okay? And today in class, we explored these different discontinuities or breaks in the graph, and there were really two different types. We saw where some of the functions had a vertical asymptote, and we saw some functions that had a hole. So this is what happens when the function is undefined. It creates a break in the graph, and those breaks are either going to be a vertical asymptote or a hole in the graph. Okay, now, so the vertical asymptote and the hole are what we call discontinuities. But a little bit more about discontinuities in functions. There are really two major types, removable and non-removable. So a removable discontinuity is basically a hole in the graph, and sometimes we call it also a point discontinuity, but all I'm referring to is a hole in the graph. And so here's an example of a graph that has a hole in it right here, which would mean, let's say we were finding the domain. The domain would be x cannot equal 1. The function is undefined when x equals 1. Which creates that hole in the graph. Now, the other major type is called a non-removable discontinuity, and there are really two non-removable discontinuities. The first one is an infinite discontinuity, which is a vertical asymptote. So you can see in this graph there is a vertical asymptote at 1, which means the domain is x cannot equal 1. Which again created that break in the graph at x equals 1. Okay, the other non-removable discontinuity is what we call a jump discontinuity. Honestly, the jump discontinuities come up more often in piecewise functions. So as we're graphing rational functions, we're not going to really run into many jump discontinuities. But in the future, you will run into jump discontinuities. But again, they're more specific to piecewise functions. Now, a little bit more about the meaning of removable and non-removable. You can think of those terms also as like the severity of the discontinuity. So like a hole in the graph is not as severe as a vertical asymptote, okay? And in some cases, like, think of the hole as like a problem. Like, we could remove the hole by just redefining the function at that value, but you really cannot remove a vertical asymptote, okay? So again, think of removable and non-removable as like the severity of the discontinuity, okay? All right, so Now let's talk about, how do we determine when the rational function has a hole, and how do we determine when the rational function has a vertical asymptote? Well, remember, this is all related to the domain of the function, okay? So recall that the domain of a rational function is all real numbers except the zeros of the denominator, okay? So remember, we have to exclude those values of x that if we were to plug them in, are going to give us 0 in the denominator. Okay, so here's an example of a more complicated rational function. Again, we're just dividing two polynomials. To find the zeros of the denominator, you would want to factor the polynomials. So if I factor the numerator, I get 3x minus 2 times x minus 1 over, and if I factor the denominator, I get x minus 4, x minus 1. Okay, so what are the zeros of the denominator? The zeros of the denominator are positive 4 and 1. So the domain of this function is x cannot equal 4 or 1. Okay, or we're saying the domain is all real numbers except 4 and 1. So these are the values of x where the function is undefined. So then our next goal would be, okay, what's happening in the graph at those values of x? Does the graph have a hole, which is a point discontinuity, or does the graph have a vertical asymptote, which is an infinite discontinuity? Well, let's see how we can figure that out. Let's start with vertical asymptotes. Okay, now, you can tell when the graph has a vertical asymptote because vertical asymptotes occur at values that are zeros of the denominator, but not zeros of the numerator, okay? So again, before you'd want to figure out your vertical asymptotes, you always want to factor the polynomials, if you can, okay? So let's look at the first example. In this example, I cannot factor the numerator because it's x plus 1, but I could factor the denominator by factoring out a 2. And then I can tell, again, by focusing on the zeros of the denominator, like for instance, my domain would be x cannot equal 2, which tells me that there is a vertical asymptote when x equals 2. Okay, so this graph has a vertical asymptote. Let's look at example number 2, and again, we're going to start by factoring. If I factor the numerator using difference of squares, I get x plus 2 times x minus 2 over, factor the denominator, I get x minus 3, x plus 2. Okay, now, notice that we have x plus 2 in the numerator and the denominator, okay? Now, first of all, though, the domain of this function would be, again, zeros of the denominator. So x cannot equal 3 or negative 2, okay? But because x plus 2 is a 0 of the numerator and the denominator, there is not a vertical asymptote at x equals negative 2. The only vertical asymptote is going to be x equals 3. What actually is happening at x equals negative 2 is that there is a hole in the graph, or a point discontinuity. But because here we're focused on the vertical asymptotes, there is only one, and it would be x equals 3. Okay. Holes, or point discontinuities. So, when a number c is a 0 of both the numerator and the denominator of a rational function, the function might have a vertical asymptote at x equals c, or it might behave differently, meaning it might have a hole, okay, instead of a vertical asymptote. Let's look at this example, x squared minus 4 over x minus 2. If I factor this, I can factor the numerator. I cannot factor the denominator. But notice that x minus 2 is a factor of the numerator and the denominator. So x minus 2 over x minus 2 simplifies to 1. Okay, so for instance, this function really simplifies to x plus 2, which is a linear function. But it's going to be the graph of a line with a hole in it at x equals positive 2. So because this simplifies to a linear function, the graph is going to be a line, but it is still going to have a hole or point discontinuity. So if I were to graph the line, the y-intercept is 2. It has a slope of 1, so I'd go up 1, right 1. And then remember, at x equals 2, there's a hole. So the graph is going to look like this. Okay, let's look at some other scenarios because sometimes this can get pretty interesting. Okay, so we want to determine whether the following functions have a hole or a vertical asymptote. And where is it? So look at our first function, x minus 3 over x minus 3. Well, first of all, we could simplify this. X minus 3 over x minus 3 simplifies to 1. So this is kind of interesting because this graph is going to be a horizontal line that intersects the y-axis at 1. But, like, if you find the domain of this function, you know, the domain is x cannot equal 3 because the x minus 3 is in the denominator. So there is still a discontinuity, okay? So there's a hole when x equals 3. But other than that, the graph is just going to be a horizontal line, which is y equals 1. Okay. All right, let's look at g of x. So first of all, I would factor the numerator. So this factors into x minus 3 times x minus 3, all over x minus 3. Whew. Okay, now, the domain of the function is still x cannot equal 3, okay, because of the denominators. And notice that we could simplify this to just x minus 3. So what do you think is happening when x equals 3? Do you think the graph has a vertical asymptote, or do you think it has a hole? Well, I hope you answered that it has a hole. Okay, so because this function simplifies down to a linear function, the graph is going to be a line with a hole in it at positive 3. Okay, so the graph of x minus 3 has a y-intercept of negative 3 and a slope of 1. So I could keep going with my slope. But keep in mind that when x equals 3, we're going to have a hole in the graph. Put a hole there. So the hole is going to be right here. But other than that, the graph is just linear. Okay, now let's look at h of x. Now it looks like some of our function got cut off, but basically it's just the reciprocal of g of x. Okay, so again, let's say we factor the denominator this time. X minus 3, x minus 3. The zeros of the denominator are still 3, so the domain is x cannot equal 3. But again, the question is, okay, but what's happening in the graph at x equals 3? Is there a hole or is there a vertical asymptote? Well, this time it would actually be a vertical asymptote because if we simplify this, it simplifies to 1 over x minus 3. So guys, this graph is a basic rational function. We just practiced graphing functions like this. This would be the graph of 1 over x, shifted right 3. So it would have a vertical asymptote at 3, a horizontal asymptote at 0, okay, because your k is 0. And then, you know, it would look like the parent function. So this graph actually has a vertical asymptote at 3, where this graph had a hole at x equals 3. And then this graph also had a hole at x equals 3. Okay, so what's the takeaway here? Well, the takeaway is that you're going to have a hole in the graph anytime you have factors that are the same in the numerator and the denominator. So if you have factors the same, top and bottom, and you can simplify those factors, then that creates a hole in the graph. Unless you have that special scenario, you know, that happens with h of x, okay? Any factor that is left in the denominator is going to create a vertical asymptote in the graph, okay? So factors that you can cancel, top and bottom, create holes. Any factors left in the denominator is going to create a vertical asymptote in the graph of the function. All right, guys. Well, as always, thank you for watching, and we'll definitely practice this some more in class. But have a good night.